Okay, good afternoon. Hopefully, yeah, sounds like it's working. Um, last class I brought up Newton's fourth law, Newton's law of universal gravitation. That's an equation, I guess you could say, but as I've said, I think every class, any equation that we use in this class should be thought more as a relationship or set of relationships. Here what we have is the mutual gravitational attraction between any two objects in the universe. That's what that equation is saying. That equation is saying that any two objects in the universe pull on each other with a force that I've labeled f sub g. Any two objects. So right now, like I said, you and your neighbor are actually exerting mutual attractive force on one another. It's true. And so let's talk about what that equation is saying just a little bit more. So first of all, what Newton is saying is that force exists. It's proportional to the product of the two masses. So if I have a mass of 50 and you have a mass of 50, our masses sit up there on the top of that equation. So the force goes up with mass. So if I were to double my mass, that would double the force. It's proportional to some capital G, which we don't need to worry about. It's just it's the universal gravity constant, just makes the units work out. And it's inversely proportional to the square of the distance. So if I'm a meter from you, there's a certain force between us. If I go to 2 meters, I will reduce the force by a fourth or a quarter. And so it's proportional to the square of the distance. A couple things worth noting there. That is called an inverse square law. It comes up enough times in physics. It's good to note when they come up. The universe, for some reason, likes to exert things proportional to the inverse square. So lots of things fall off with a square of the distance. And by fall off, I mean if you were to plot the force between two objects, when they're really close, there would be a lot of force. There could be a lot of force. Well, gravity's not that strong. 2 planets or something. But then as the distance gets greater, there's this exponential decrease, and we very rapidly get to almost nothing. And so for that force to be at all appreciable, you have to be close, and you have to have a lot of mass. We don't really care what the capital G is, but it's got the units of something times 10 to the negative 11th. So it's 0.000000006 is G, I think. And that's a very, very small number. So you need a very large mass in order for that to be appreciable. Now, that said, in order to be appreciable, it's still measurable. It was in the 1700s, a guy named Cavendish actually set up an experiment in his lab. Newton was never able to experimentally determine G, but a guy named Cavendish actually did it, and it was pretty cool experiment. We have one somewhere in the physics building, where he took a very thin string, hung it from the ceiling, and then he put a bar at the bottom, and he put 2 weights at either end of the bar, so it's kind of like an upside-down T. And that bar, and he got everything stationary. You think about how he had to be very, very, very precise. So like any air currents would cause this big pendulum to move. So he had to be very, very precise. And then what he was able to do, literally just took big, I don't know, bags of sand or something like that, and put them near those 2 weights, one on one side and one on the other side of those 2 weights. And the whole thing just shifted a little bit. And it's a pretty rudimentary experiment, but it's the 1700s. They don't have access to lasers and other things that we would use today. So, but that was enough. In the lab, you could actually get 2 things to gravitationally attract, which, if you ever get a chance to see something like that, it's kind of crazy. I mean, we all know we're all attracted to the Earth. That's gravity. Okay, we're all, I could show you gravity. There, that's gravity working. Stuff falls down. But to see gravity between 2 objects and where one of them is into the Earth is pretty rare. So pretty much any gravity you typically witness, that or the force you're feeling on your seat right now, that's attraction between something and the Earth, a big planet. Even when you go look at the moon going around is the attraction between the Earth and the moon. Or when you go around the sun, that's the attraction between the Earth and the sun. So the Earth is usually one of the M's. But to see just 2 lab human-sized objects go due to gravity, it's pretty neat. But it actually happened. It's kind of cool. So anyway, Cavendish was able to measure it. One other thing to point out about that equation, again, I think every one of Newton's laws we've talked about this semester, I've said, and this is I think worth noting, they were all not just, oh wow, good job, you figured out the equation. There was always something a little bit controversial or unexpected about the equations that I think are one of the reasons that it took a while to discover them. And here's something that's definitely unexpected in that equation. What that equation is saying is that two masses, let's take two, you being one and the sun being the other, are pulling on each other. Or another way to say that is your existence is affecting the stars, I think is another way to put that. And that's a lot of hubris to be able to say that. I think that's a pretty proud thing to say, to be able to say, just the fact that I exist is pulling on the distant most stars. That I actually, my influence extends to all infinity. That equation only equals 0 where r equals infinity. Remember limits from pre-calc or something? That's the only time that equation is 0. If you want to get far enough from me that I have no gravitational effect on you, you have to go to infinity or beyond. And that's the only place you can go where there's no effect. And that's a profound statement to say that the farthest star in the galaxy is being pulled on by me right now. I affect the stars. Or that equation doesn't have like here's how this equation works on Earth, and here's how this equation works in space or somewhere else. It's just one equation for the universe. These are universal laws. And so what Newton is saying is that there isn't a curtain or any kind of boundary between the terrestrial and the celestial. So those are really, it's just one universe. And I think that we weren't really totally sure about that idea in the 1600s, that is just one universe and the same laws govern it. And I don't have to have laws that work on Earth, laws that work for men and laws that work for animals and rocks or whatever. It's just one universe with universal laws that govern it. Okay, and then the last thing that came up last class that I really wanted to hit on today is that this equation is the mutual attractive force between any two objects. Most of the time, where we care about that equation is when one of those m's is the Earth, and the r is the Earth. So let's get out my chalk again. And so here's the Earth, here's me and you right there. We are not touching the Earth, at least in terms of that equation. The distance between me and the Earth right now isn't 0. The distance between me and the Earth is approximately 1 Earth radius. That's about how far I am from the Earth if I want to use that equation correctly. So it's something like 6,000 kilometers, I think. It's pretty far. So that's a pretty big number. So I've got a pretty big number on the bottom and a little number that is a capital G. But fortunately, the Earth is very, very, very unfathomably large. It has a lot of mass. Something like 10 to the 24th kilograms. It's a lot. So that's I won't do the 000 thing, but it's a million kilograms. So take a million kilograms and a million of those, and then a million of those, and a million of those. It's a lot. It's big. Okay. So that's how far away I am. And hopefully I can write somewhere where everyone can see the gravitational force between anything on the surface of the Earth. All these things, I'll call this mass of the Earth, and this is r, radius of the Earth, and this is mass of whatever I'm worried about. All of these numbers don't change. So when I want to know the gravitational force between the Earth and this piece of chalk, the Earth and me, the Earth and you, for all of those calculations, we always use capital G, we always use mass of the Earth, we always use radius of the Earth, if you're on the Earth. Now, the radius of the Earth is big enough, thousands and thousands of meters, that doesn't change much if I'm on the first floor of the building or the second floor of the building. It actually does change, but not much. So you have to go really, really, really far away until that becomes appreciably different. So G is a universal constant. That's just that works for the whole universe. Mass of the Earth, we'll treat as pretty constant. It is. I guess every time there's a comet impact, this goes up by a tiny, tiny bit. Every time we shoot someone off into space, it goes down a little bit. But it's pretty much constant. And then the radius of the Earth is also pretty constant. Now, the Earth is not a sphere, so that's probably more significant than what floor of the building I'm on. The Earth isn't a sphere. Because it's spinning, actually, it actually is fatter in the middle. You can imagine something that wasn't rigid spinning around. It actually kind of flattens out a little bit. So if you want to weigh as little as possible, I would go to Ecuador, go up to the top of a mountain. I think those are your best options to get as far away from the center of the Earth as possible. It's not going to still going to be much effect. But so all that to say, all that is pretty much constant. And these three terms, now let's see if you can think back to Newton's second law, F equals ma. If I have an F and this is an m, this must all be an a. And it is. This number times this number divided by this number squared turns out to be an acceleration. That turns out to be an acceleration. So these three numbers all boil down to an a. So this equation works out to be F equals ma. And it's a particular, like I said, because these are all constant, it's a particular a that we call lowercase g. Hopefully somewhere in your science life you ran into 9.8. That's the acceleration due to gravity. The acceleration due to gravity, that 9.8 you may have heard of, and for this class 10 is close enough. That acceleration due to gravity, measured in meters per second squared. All accelerations for us are going to be measured in meters per second squared. That acceleration comes from the product of those three numbers. So that 9.8 you may have heard of before, that's the acceleration due to gravity. That's the acceleration due to gravity on the surface of the Earth. So that capital G, again, is constant everywhere. But if I'm not on Earth, then those other two numbers aren't the same. Question? That's a great question. The question was, is it 9.8 or negative 9.8? Let's see. For us, I would like us to know it's around 10, and the sign isn't that important. Where it would be important, and I don't know if this will ever even come up in this class, is if I'm doing a problem, I want to calculate the velocity of my car keys after I throw them off a cliff. In order to do that problem, I should probably define a coordinate system. And coordinate systems are arbitrary. So the other day, I made me the origin of this classroom. So this 0, 0, 0. And so you would be, I would call you positive something, and even in the z-axis. If I call down negative and up positive, which is convention, then gravity would cause things to accelerate in the negative direction. So I would use negative 9.8 to make my math work out. So I would use negative 9.8 if negative means down, or more technically pointed toward the center of the Earth. So in this classroom, if I wanted to know what is the velocity of this, well, yeah, let's do a little tiny bit of math. If I want to know the velocity of this 1 second after I drop it, that was maybe a second, not quite. If I want to know the velocity that 1 second after I drop it, here's how I can figure that out. I know its acceleration is 9.8 meters per second per second. That's what meters per second squared is. So what that means is that acceleration, anything in free fall near Earth, anything in free fall will change its velocity, accelerate, change its velocity, 9.8 meters per second every second. So when I let go of that thing, 1 second later it was going 9.8 meters per second, which is about 22 miles an hour. So take anything, it doesn't matter, right? The car keys or a car, throw them off a cliff, 1 second later they'll be going 22 miles an hour or 9.8 meters per second down. And if I want to use velocity, velocity has a sign associated with it. I would want a coordinate system. I might say, okay, the cliff is 0, anything below the cliff is negative. And so my car is moving in the negative direction. It's moving negative 9.8. And a second later, it's moving negative 19.6. And a second later, negative 29.4. And it's speeding up 9.8 meters per second every second. Question? Good question. Is there a limit to how fast something could fall, or is there a limit to how fast something can accelerate? Both good questions. Or I don't know which one of those are your questions. I'll try to answer both because those are both interesting. Yes and yes, there is a limit. Let's first talk about, is there a limit to how fast you could go? So if I drove my car off a cliff, it would be accelerating at 22 miles an hour every second. That's weird units, but I'm used to miles per hour, so we'll do that for a second. So it'll accelerate 9.8, which is about 22 miles an hour. So 1 second after it goes off the cliff, it's going 22 miles an hour. And 1 second later, it's going 44 miles an hour. Another second later, it's going 66 miles an hour. After an hour, it's going about 80,000 miles an hour. Here's the limit. We're talking about the acceleration due to gravity on Earth. It will have gone, I can't dig a hole that deep. So if I were to dig a hole straight through the center of the Earth, my car would accelerate into the hole, and then by the time it got to the middle of the Earth, it would be going, 70 or 80,000 miles an hour. And it would actually then slow down and then just peak up somewhere in the Indian Ocean, and then it would come back here. So it would oscillate forever until maybe air resistance. So the limit of acceleration is kind of limited to what's doing the accelerating. If it's a planet, you can only accelerate till you get to the center. So go to Jupiter, dig a hole to the middle, and that'll be as fast as you can go. You'll get to the middle, and you'll start slowing down. Now, if you were not on a planet and you were just accelerating out in space, either with thrusters or toward a black hole or something, your limit is the speed of light. You keep speeding up till you're going 186,000 miles a second. That's the speed of light. So, and that you would reach that, you would never get there. You can never get to the speed of light. You would reach that sort of asymptotically. You would almost. You could get maybe, if you were going toward a black hole, maybe you could get up to 0.9 the speed of light. I don't know. Our universe has limits in terms of speed. Nothing can go the speed of light except light and other massless fields and particles, things like that. But if you have mass, you can't accelerate instantaneously, and therefore you can't go crazy fast. Which, by the way, not really the scope of this class. Is a bummer that our universe is so big. If we ever want to visit another star, it's just going to take forever, and that is a big bummer about. We could have the nicest rockets in the world and get us up to the speed of light. So say we could get to 0.9% the speed of light. So we're going 180,000 miles a second. That's fast. And it'd still take a lifetime to just get about anywhere. That's the bummer. Our universe is just so big. One day we're going to get a signal from an alien race that says, "Hey, we're here. We just caught your first radio transmissions. I love Lucy," or whatever. And we'll radio back, "Cool." And that two-way communication will, take a million years. And so we'll have gotten their communication. They'll probably be dead and gone by the time we receive theirs. And we'll shoot a reply back, and they'll be dead and gone we'll all be dead and gone, but both civilizations will be dead and gone, and we'll miss each other. So not to be depressing. Just, the lesson is make friends here, because this is probably all we got. Okay. Question. Yes. That is a great segue. Yes, I would love to talk about skydiving. Let me just reiterate one thing and we'll talk about skydiving. And the thing I want to reiterate is, here's your one of the lessons for the day. Everything on Earth accelerates down to 9.8 until we get to skydiving. So everything accelerates at 9.8. And maybe mathematically, if you care, really, Let's see. I don't need to explain it. Well, everything's acceleration is F over m, right? We know that's Newton's second law of rearranged. A equals F over m. Take this equation, and so this is the force. This is the force that anyone's feeling. That equation right there. That's the force that we all feel, regardless of what you're talking about. All of us feel that force. Cancel your m out of the situation. Cancel your m out. In other words, take that force, cancel your m out. We're all going to accelerate at 9.8 meters per second. So that's just fixed. You're pretty much no way, but I should say this way. Neglecting air resistance, we're all going to accelerate at 9.8. So when I step off that cliff, air resistance is a velocity-dependent thing. You have to be moving. Stick your hand out of the side of a parked car, you're not going to feel a lot of air resistance. But as soon as you get going pretty fast, air resistance becomes appreciable. So stick your hand out of a car going 100 miles an hour, you'll feel that. And it goes up with velocity. So let's talk about, this is such a good segue. It actually happens to be our first iClicker question. So let's have our iClicker question. Here it is. I think it was like 2 years ago. Did you guys see that guy, Felix Baumgartner? Red Bull sent him up on a balloon and he jumped off. It was crazy. So he rode a helium balloon, I think it was. I think he rode a helium balloon pretty much to space. I mean, you can't take a balloon into space because balloons need air to float on. But he pretty much was in space. He was as far as you can get in a balloon. So last time you accidentally let go of a balloon, it went up. That's where Felix Baumgartner jumped from. He jumped from there. And he sped up, as things do as they fall toward the earth. He jumped from there and he fell. Before he pulled his chute, I want to know what you think his velocity plot looked like. So all four of those start at 0. I think that was his velocity when he jumped. He didn't like rocket down or anything. So he started at 0 and he sped up in the negative direction. So I'm calling negative down here. So he started 0 and started moving in the negative direction. So there's 4 options for what he did. See if we think what we think Felix did. This is before he pulls the chute. Yeah, before he pulls the chute. Take about 15 more seconds. You would count air resistance. We're up to 208 people. That's good. 2-9. All right. Well, there we go. Let's take a look at what people said. It is surprising. Let's take a look at the options. So, if there were no air resistance, the answer would be D. If there were no air resistance. And so just about everything you watch ever fall off of something, D is what it does. Last class I threw the basketball up and I got the software to plot it for us. Straight line. Because most things, yeah, I think that's a fair argument. Most things don't experience significant air resistance and they just accelerate at 9.8. So if I were to jump off a cliff, 1 second later, I'd be going 9.8 meters per second, and then 1 second later, I'd be going another 9.8, 19.6. Baumgartner did experience air resistance, so it slowed his acceleration. And you would think it's C. C is actually what most skydivers look like. So here's what most skydivers look like. So there's my car keys. There's my car keys, no significant air resistance. If you were to jump out of an airplane, right at the beginning, you would be accelerating just like a set of car keys. But pretty soon afterwards, you're going to start experiencing significant air resistance. That's going to slow your acceleration or reduce the slope of this line. And so a skydiver does this, where we typically call this the terminal velocity. That's what most skydivers do. So what happens to most skydivers is they start accelerating at 9.8. When you step out of that airplane, you feel like you just jumped off a cliff, or you just feel like you normally do in normal acceleration. But that normal acceleration diminishes as more and more air resistance occurs, and you eventually reach terminal velocity, which maybe we'll talk a little bit more about in a second. Baumgartner actually did B. And yeah, and I know, it's crazy. And here's why. It's weird. It's very weird. It's unexpected. It's unexpected. But here's what happened. He stepped out of that airplane. No, it wasn't an airplane. You couldn't fly up there because there was almost no air. He stepped out of his crazy balloon, and there was so little air, he accelerated at 9.8. Then he actually slowed his acceleration once he started encountering the air, and he actually slowed down. He actually slowed down. His velocity went back up. Then he reached terminal velocity. So it's like a backwards situation. And the reason it's backwards is when he jumped out, there was almost no air. So he jumped into pretty much empty space, and his acceleration was 9.8, and then he started encountering the atmosphere. He started encountering the atmosphere. As he encountered more and more atmosphere, he actually slowed down. And that's the curve going back that way. Yes? Yeah, let's see, 300 seconds. Yeah, basically C is kind of the tail end of B. It's somebody reaching there. Yeah, so a skydiver reaches, well, depending on what squirrel suit or doing this, I don't know, but they reach terminal velocity pretty quick. Well, like I said, yes, C is someone reaching terminal velocity. Oh, yeah, and then B, he reached it kind of from below because he got faster than terminal velocity and had to kind of go back to it, which is weird. And you're only allowed to do that if you're up in space above the atmosphere and then re-entering the atmosphere. And so most skydivers jump into atmosphere. Most skydivers jump out of planes, and those planes are very atmosphere dependent. You can't fly a plane where there's no atmosphere, lift and things like that. So yeah, most skydivers just approach their terminal velocity. He actually exceeded his terminal velocity and had to come back to it, which is a little bit crazy. Yeah, that's a crazy one. Question? Yeah, when he first jumped out, there was almost no air when he jumped out. There had to be a little because he's in a balloon, and the balloon is buoyant on the atmosphere, but crazy thin atmosphere up there. Yeah, that's a weird one. And so interestingly, he broke the sound barrier twice. Once on the way down and slowing back through it. Crazy. So he was going faster than the speed of sound. At that altitude, speed of sound is around 700 miles an hour. So I think he went like 800 or something. Question? Yeah. The question was, did the balloon stop? Yeah. They pretty much built a balloon. That's a really good question, actually. Let me draw a diagram that would work for the balloon and Felix. So let's draw, here's Felix here. Okay. Here's a diagram. Here's a diagram of all of the relevant forces on a guy or a girl as soon as they jump out of an airplane. We're going to call that weight. Oh, and by the way, I mentioned that in this class I want to try to be accurate about terminology. That thing you're feeling right now that's pulling you down into the chair, that's not called gravity usually in the physics world. We usually call that weight. Weight is the force due to gravity. There's a good term to know. So gravity is that acceleration that, coupled with your mass, creates something you call weight. So weight is the product of your mass times gravity, which is a special version of Newton's second law. So Newton's second law says F equals ma. there's a special version of that. Weight equals mg, weight's a force, m's an m, and g's an acceleration. Yes? No problem. For us, so gravity is, again, it's just so many of the physics terms we use in everyday language. Let's be specific. For us, gravity is an acceleration due to, well, let's see. Yeah, due to a planet, I think is usually, that's maybe too specific. This acceleration due to just the presence of another mass. So I would define gravity as an acceleration. That's important. And so weight is a force due to this acceleration called gravity. So there's F equals ma, and right above it, a particular force called weight and a particular acceleration called gravity. Yes, sir? Oh, yeah. That is a fine sidetrack. That's good. The question was, did he experience G's? Yes. In fact, that's a good term to know. So when you ever hear that term, oh, I pulled a lot of G's or something, that is, 1 G is 9.8. So a G is just a proportional to what we typically experience as gravity. So when you, and we'll probably talk more about this later in the semester, when you drive over a hill, you feel less than a G. You feel a little bit weightless. You kind of come out of your seat a little bit. You're feeling less than G. When you go in the bottom of a hill or the bottom of a roller coaster, you feel heavy. You're feeling multiple G's. So if you were sitting on a bathroom scale and riding on a roller coaster, sure. At the bottom of the hill, the bathroom scale would read more than your weight. Say it read double your weight, that means you were experiencing 2 G's. 1 G, because you're on Earth, and another G from the motion of the roller coaster. So fighter pilots experience up to 8 or 9 G's, I think, sometimes, or astronauts are expected to be able to survive that. And the reason is, when you're taking a really tight turn, you're experiencing more acceleration than just what you're typically used to walking around in. So here's how that affected Baumgartner. He wasn't flying in a plane, but he started spinning. And you can imagine, I think you could imagine that if you start spinning, you start the fluid in your body starts to get flung out to the edges. And if you're spinning about your belly, your feet and your head are going to start to feel swollen and expand a little bit. And that's, you could measure that in G's. So right now the blood in my feet is experiencing 1 G. If you were to swing me around and the blood could feel multiple G's. And there was a risk that when he jumped out, once he started running into the atmosphere, if he started rotating too fast, you could get too much blood in your head and you pass out. And I think they had calculated the number of G's he could experience before that happened. And when you watch the video, he tumbled. He did, I don't think he actually passed out. I think he didn't. Yeah, I think he made it. But I think they had some measure of, like, I don't know, waking back up halfway through or something. Yeah. Okay. Very good question. So here's a diagram of all the relevant forces acting on someone that just jumped off a cliff. And what happens is slowly a little other force shows up. That's your air resistance. So right after you jump off the cliff, not that significant. As the air resistance grows and this gets bigger and bigger, eventually the air resistance, we'll call it force of drag, FD, force of drag, eventually that actually cancels out your weight. And a term I don't think I've used since day one, which we all need to know, your net force is 0. That's a good definition of terminal velocity. And here's why. You've reached your terminal, meaning finishing, velocity when you're not accelerating anymore, right? Because acceleration is the change of velocity. If you're not changing your velocity, you're not accelerating. Well, according to Newton's second law, how can you not accelerate? You have to have no force. Maybe a better way to write Newton's second law is to say F net equals ma. So that is actually something I did want to talk about today. Right now, most of you right now, as you're sitting here, are not accelerating. You're not changing your velocity. You are pretty much at equilibrium. Equilibrium meaning no net force. So you're not accelerating, not because there's not any forces on you, it's just because they all cancel out. So right now, as we're all sitting here, we're experiencing weight. We're not weightless. We all have weight, but we're not falling through the floor because our seats are canceling that out. So this diagram I have up here is the diagram of something in equilibrium, meaning all the forces cancel out. So Baumgartner jumps out of his balloon. He feels weight. He accelerates till eventually air resistance cancels that weight out, and he stops accelerating. He reaches terminal velocity. That is also the diagram of his balloon. His balloon, when he first left the Earth, had a buoyant force up, and he accelerated up. And eventually, and he had weight down. So his weight down, buoyant force up. He wouldn't have gone anywhere if those were equal. So fortunately, his buoyant force was greater than weight, and he accelerated up. And so he starts accelerating up, and as the atmosphere thins, he has less buoyant force, and eventually the buoyant force decreased to where they're equal. And he'd reach, then he could just hang out there all day, and he wouldn't get any higher. So most balloons, unless they burst, will do that. Will reach a sort of an equilibrium point. If you think about, have you ever seen something float in the middle of a pool or in the ocean or something? It's neutrally buoyant. It's not going up or down. And you can do that in air. So you can imagine, I don't know, maybe you've seen a balloon that, you get those, you get a balloon in your house, you have a helium balloon, and it's floating on the ceiling, and a few days later it's just hanging out right in the middle. When it's deflated a little bit, it's just hanging out right at your head level. That's a neutrally buoyant balloon. It's buoyancy, and it's got weight down and buoyancy up, and they cancel out. Okay. Yes? Right. No net force. So the question was about, do you remember the homework? You're pushing a chair, was it? Something. You're pushing or pulling a chair, and the key to that question was at a constant velocity. So constant velocity means you're not changing your velocity. If you're not changing your velocity, your acceleration is 0. And if your acceleration is 0, there must either be no force or no net force. So they cancel out. And so when I got a chair up here. So when I'm pulling this at a constant velocity, I can feel I'm pulling. It's going at constant velocity. And the only reason it's not accelerating is because the friction on the floor and me are canceling each other out. And so if you want to pull something at a constant velocity, you have to cancel friction. Or when you're driving down the road at a constant velocity, it's not that there's no forces on you. I think you have to put a little bit of gas. When you're going at constant velocity, it's just that the air resistance and other rolling resistance, things like that, opposing you are being canceled by the other force, friction force. Yeah, that's a good question. So yeah, one of the things I definitely wanted to make sure we all got today is the concept of net force. And net force is just the sum of the forces. And so if you're not accelerating, you have no net force. You could have 45 forces on you, they just all cancel out. So you can imagine when you're playing tug of war and no one's winning, the net force is 0. They're all canceling out. Yep. Mm-hmm. He'll slow down. Yeah, that's a really good question. The question was, if you were, say you were in a plane and that plane was just full throttle down and you jump out and you are already going faster than your terminal velocity, you'll slow down. You'll slow down to that terminal velocity. Yeah, that's a good question. And there's lots, and so your weight is constant, and that's mg, or mass times 9.8. But the thing pulling you up is dependent on how fast you're moving. So, like I said, put your hand out of the window going 100 miles an hour, or parked car, you're going to feel a lot of different. And also, if you put your hand out of the window, change the orientation. You're going to change the force a lot also. So that drag force, that F capital D, is dependent on your velocity. It's dependent on what you're falling through. Is it water, syrup, air? And it's dependent on how big you are. So guys wear those squirrel suits, or guys try to go really fast like that with a slick suit. I don't know. It depends on your shape and how you're oriented, things like that. Okay. 10 minutes left. Let's move on to one other thing real quick. Let's see here. Yeah. I brought up Newton's third law, I think 2 classes ago. And I keep getting these things out here to demonstrate it, and I never get to it. So I want to at least get to one of them today. And so this is our, we did 1, 2, we kind of did 1, 2, 4, now 3. If we can just talk a little bit about Newton's third law, we'll be done with Newton's laws. We can do some other stuff. That'll be good. And Newton's third law is another one of those I think is a little bit counterintuitive, and it's stuff pushes back, or sometimes phrased, if object A pushes on object B pushes back on object A, and equal and opposite, that phrase you may have heard before, equal and opposite. So what that means, and again, this is counterintuitive, all forces, this is true of all forces come in mutual and opposite pairs. All forces. So let's talk about some examples. Right now, you are feeling pulled into your chair because the earth is pulling down on you. The earth is pulling down on you. That equation. The earth is pulling down on you. Well, guess what? You are pulling on the earth equal and opposite. You are pulling on the earth equal and opposite. It is a mutual attractive force. So there's no way to ever, as far as I know, push on something and not have that be mutual. And so right now, the earth is pulling on you. You are pulling back on the earth exactly the same force. If there were a fly coming into this room right now, and I were to swat that fly, I could hit the fly. I would apply force to the fly. That fly would actually push back on me with the exact equal and opposite force. It can't not be true. And the only difference would be, so let's see, where's my equation? I erased it. Well, I'll put it back. I'm running out of chalk. So the equation I had up here a second ago, the only reason when I swat the fly, the only reason I don't go accelerating away from the fly is because I have a lot more mass. We experience the same force. The fly and I actually experience the same force. I'm just more massive, so I don't accelerate as much. The fly ends up being the one that accelerates. But those forces are always true. Those forces are always equal and opposite. So one demonstration I have of that up here, are my little hoops. These little hoops will show you how much force they're experiencing by how much they deform, right? So these hoops will show you how much force they're experiencing by how much they deform. And this is probably the last thing we talk about today. And that is, if I were to push on this whole system, hoop, green thing system, this is one big hoop, green thing system. If I push on this and this whole system doesn't move, the whole system doesn't go anywhere, it experienced how much force? No net force, right? So this whole system doesn't go anywhere. Well, the reason it doesn't experience any net force is because I pushed here and the table pushed back equal and opposite. So this whole system is not accelerating because there's equal and opposite forces. Okay. If that's true, this green thing is pushing back equal and opposite to me. So if I were to look at just the hoop system, I can see that the system is not accelerating anywhere. That's because I'm pushing this way and the green thing is pushing back equal and opposite. So I know that over here there's a force equal to my force. And then if I were to look at just one of the hoops, notice they are right now are deforming the same amount. I can conclude that they're experiencing the same net force. Both are experiencing this much, right? Because I'm pushing on the left side of this one, and then the green thing's pushing on the right side of that one. So they're both experiencing the same force from the side, and they're experiencing the same force in the middle. The mutual force is exactly shared right there in the middle. So sometimes there's a thought that like my push is making it halfway through, or my push is being diminished, or my push gets absorbed. None of that's really happening. It's just a series of things pushing back equal and opposite. So my force shows up here. That force is equal and opposite here, and then there's another force equal and opposite over there, and nothing is accelerating anywhere. And so that hopefully will give you one quick demonstration of that everything's always mutual, One last thing, I'm gonna take today's iClicker grades and last class iClicker grades, re-upload the gradebook to Colab. Please check, make sure you're getting graded. See you Wednesday.